So we are seeing first of two cases. First case, when current in one coil is produced because of another coil. Second case, the current induced in the coil itself due to flux change. So second case we will see later, that is called self inductance. First we are seeing this mutual inductance, that means current induced in one coil due to another coil. So we have already seen the figure and we have reached up to this point. N1 phi1 is equal to M12 I2, where M12 is called mutual inductance of solenoid 1 with respect to solenoid 2. So why do we need? Because current is I2, not current I1. So current is flowing in outer solenoid or bigger solenoid, and we are seeing the flux inside coil 1. So we need a constant which converts this current into flux related to first coil or smaller coil. So what is that? That constant is M12, mutual inductance constant. Now let us see what is there. Now for these, since these are simple coaxial coils, because the axis is same, for these simple coaxial coil it is possible to calculate M12. So let us calculate how we calculate M12. The magnetic field due to current I2. Okay, so we are calculating the magnetic field due to current I2 in solenoid 2, because current I2 is going through in this bigger solenoid. So what is magnetic field? Magnetic field is B0 is equal to mu 0 Ni. Now B0, because since there is no material, so let us write simply B. So this B will increase when some material is filled inside. Mu 0, again no material is inside. Now we are talking about second coil. So this is N2 and current is I2. So what is magnetic field? Mu 0 N2 I2. Okay, the resulting flux linkages with this coil S1. So how do we calculate flux? So flux is equal to N was constant, flux. So this is flux in first coil due to magnetic field of coil 2, or let me write it B2 for. So here what we are seeing, flux linkages due to current I2. And why flux is linked? Because there is a magnetic field inside this smaller coil also, because this smaller coil is inside this bigger coil. So N1 phi 1 is equal to, so what is the N1? So we know this small n1 is equal to capital N1 upon L. So L into N1. N1 into L, this is the value of N1. And what is the phi? Phi is BA. Now what is the magnetic field? Magnetic field is mu 0 N2 I2. So let me write this, mu 0 N2 I2. Now what is the area? Since we are considering only for the smaller coil, so the area we will take for this smaller coil. For coil, area is pi, radius of this smaller coil is R1 square. So this is the total equations, N1L pi R1 square and this magnetic field. So this is we got. So let us calculate this. So mu 0 N1 N2 pi R1 square and this L length and this current I2. So this we got. Okay. So this we got. When we compare this with this equations, so I2 gets cancelled out. So what is the value of M12? M12 is equal to mu 0 N1 N2 pi R1 square L. So M12 is equal to mu 0 N1 N2 pi R1 square L. So this is the value of M12. So this is the mutual inductance in coil 1 due to coil S2. So this is value of M12. Note that we have neglected the age effects, because age is, you know, magnetic field is not simple, but we have neglected, assuming that solenoid is very long. and we have assumed that this magnetic field is uniform throughout the length and width of the solenoid. This is a good approximation, keeping in mind that solenoid is long. So we have considered this solenoid is quite long, and this is the uniform magnetic field inside the coil. Now let us consider second case. Now we consider the reverse case. Now what is happening? Instead of flowing current in outer solenoid, a current I1 is passed through solenoid S1. So this time we are putting some current in this smaller solenoid. So in this case, similarly, so the flux linkage with coil S2. So since this coil is inside this outer coil, so there will be some flux linkage with the outer coil as well. So let us see what is this. N2 phi 2 is equal to, now this constant is reversed, M2 1, and current is I1 because current is flowing in inner coil, and flux linked is with outer coil. So N2 phi 2 is equal to this constant into I1. What is this constant? This constant is making this current is converting this current into linked flux for this outer coil, where M21 is called mutual inductance of solenoid S2 with respect to S1. Please remember this 2-1. So this is mutual inductance of 2 with respect to 1. Previously it was M12. That means mutual inductance of 1 with respect to 2. Now let us calculate. So again same thing, we will try to calculate this M21. So N2 phi 2. So what is the value of this N2? N2 is very similar. We get N2L. Again, since the area of this smaller coil is that which is common, so again we take the same area. Area will be taken same because outside this coil there is no magnetic field. Previously we were considering only this small area because we want magnetic field inside this coil, magnetic flux with this coil. Now in the second case, when we need magnetic field, again we are taking the same area. Why? Because we know magnetic field outside coil is 0. So we take only this much area. So area will remain same, pi r1 square. Now current is passed in first coil, so mu 0, n1 number of turns in first coil, I1. So what do we get? Number of turns into length for solenoid 2, area will remain same for a smaller coil. Now magnetic field associated with this smaller coil mu 0, number of turns n1 into current I1. If you calculate this or compare this, so let us compare M21 this with this. So what we get? M21 is equal to mu 0, okay. So I1 and I1 gets cancelled out. So mu 0, N1 here, N2 here, and pi R1 square, pi R1 square, this is M21, pi R1 square into L. So this is we got. If you compare it with M12, so mu 0, N1, N1, N2, N2, pi R1 square, L, L. So both constant M1 and M2 are same. Both are same. So here N2L is the number of total turns in coil S2. M21 we have already calculated, and what we have seen, M12 is exactly equal to M21. Both the mutual inductances are same, and we put a constant value M. Both the mutual inductances are same. Why these are same? Because the area will remain same. Common area is same. So we have demonstrated this equality for long coaxial solenoids. However, the relation is far more general. That means we can use this relation in any case. Note that if inner solenoid was much shorter and placed well inside the outer solenoid, then could still have calculated the influx N1 phi 1, because of the inner soil is effectively immersed in uniform magnetic field due to outer solenoid. So what they are trying to say, suppose this is outer solenoid and this is inner solenoid. Since inner solenoid is very small, and you know that magnetic field inside bigger solenoid, especially in the middle, is quite uniform, so we can easily calculate this flux linkage. But problem will comes in that case, calculation of M12 would be easy. So this is first case. However, it will be extremely difficult to calculate the flux linkages with the outer solenoid. Why? Because when we are passing current in this inner solenoid, so there will be this type of flux in outer solenoids, which will make the case very difficult, as the magnetic field due to inner solenoid will vary across the length. So this will vary. For inner solenoid, this magnetic field will vary too much, that calculation would be very difficult. But this formula is true, and we have used very simple manner where we have proved this using some assumption, but it is true. So as the magnetic field due to inner solenoid would be vary across the length as well as cross section of the outer solenoid, therefore calculation of M21 would be extremely difficult in this case. In second case, when current is passing through this small coil, the equality M12 is equal to M21, this equation is very useful in such situations. So this is something where what we have proved, because it was very simplistic case where we took two coaxial solenoids. We explained the above example with air as medium. So we have not considered anything filled inside within the solenoid. Instead, if a medium of relative permeability mu r had to be present, the mutual inductance will be changed. We simply multiply with this mu r as well. Mu r. It is important to know that mutual inductance of a pair of coil, solenoid, etc. depend on the separation as well as their relative orientation. So that means geometry also affects. So this is about mutual inductance.